Okay, one last time. Now, I'm trying to shoot this video about 3 different times. My camera's let me down each time, so let's hope this is the last one. What am I doing? I'm doing 3.6 from the textbook, approximating a binomial by normal, right? So generally, this topic's called binomial to normal. All right, so it's 3.6, page 53. What are we doing here? We're going to replace a binomial, or approximate a binomial, better to say, with a normal distribution. Why do I want to do that? Because sometimes, especially when n is large, working out binomial probabilities is time-consuming and difficult. So, here are the rules. If n is large, no point doing it otherwise, and p is close to 0.5, why? Because that keeps the binomial distribution symmetrical, and you know that normal is symmetrical, so that's good. We can approximate x, which is binomially distributed with n events and p probability, with a normal distribution mu and sigma squared, where you already know what mu and sigma squared are, mean and variance respectively. Mu would be np, literally np is the number of events times the probability, and your sigma would be the square root of np 1 minus b, and that's sometimes written as npq, where q is 1 minus b. Okay, so far so good? I hope so. What I'm going to do is just show you a quick example 11 as given in the textbook. Then I'm going to talk to you about continuity corrections, and then we're going to do a couple more examples, and that's us done for today. Right, example 11. So here we've got something where the probability is 0.53 and n is 100, so n is large enough. Write down a binomial model. X is binomial with 100, 0.53. You can approximate it with a normal because n is large and p is close to 0.5. And your distribution would literally have mu of 0.53 times 100, and your sigma would be npq, or 100 times 0.53 times 0.47, all square rooted. Right, I hope that seems relatively simple for everybody. Right, part 2, we'll talk about continuity corrections. Because we're dealing with something that's a binomial to normal, so a discrete, which binomial is, to a continuous distribution, we have to do something called a continuity correction. And while it's incredibly kind of awkward in many people's eyes, I actually find it really simple if you understand how numbers work. So I'm going to give you 4 examples. They all look very similar. That's done on purpose, so you will understand what each of the different things mean. So the first one, if you've got binomial land x is less than 10, in normal land, that is x is less than 9.5. Why? Because binomial is discrete. You can only have things like 9, 10, 11, but normal is continuous. So you need to find the number, the smallest possible number that would round up to 10, and that would be your boundary. 9.5 would round up to 10, so you can't be 9.5 or bigger. Next one, x is allowed to be 10 this time, less than or equal to 10. So the smallest number that this can't be is 10.5, because 10.49, etc. would round down, and you're allowed to be 10 this time. Third one, x is greater than 10. Well, x has to be bigger than 10, but 10.5 would be the largest number, the smallest number you could be sure of that wouldn't be rounding down to 10 in the binomial land. Yeah? Because 10.49 would round down to 10, and you're not allowed to be 10, you have to be bigger than 10. So that's why it's 10.5. And then finally, this one here, I hope you don't get seasick because I'm moving the camera so much. X is greater than or equal to 10, so this time we're going to go for 9.5, because 9.5 is the biggest one, the smallest number rather, not biggest number, smallest number that would round out to be 10, and we were allowed to be 10 this time. We can't be 9.4 because then we'd be something rounding down that's less than 10. Okay, hope that makes sense. Now I'm going to look at example, first of all I'm going to look at example 12, so let's have a look at example 12 first. Because example 12 shows us in much more detail, well not much more detail, just some detail of how this continuity correction business works. So here we've got first one, its probability if x is less than or equal to 70. Well, if we're allowed to be 70, 70.5 is our upper bound, because obviously 70.5 would round you up to 71, so you can't be bigger than 70.5 if you want to be 70 or less. All right. The other one, 80 to 90, is a much more interesting kettle of fish, because you notice 90 doesn't have the equality bit underneath it, so it's less than 90. So let's just do the 80 bit. Obviously it's 80. If you're allowed to be 80, the smallest number you can be is 79.5. So if you want to be 80 or more, 79.5 is fine as a lower bound. Now the 89.5, why is that? Why is that not 90.5? Well, the logic is you can't be 90. And 89.5 is the number that was one way you start rounding up to 90. So that's why that's 89.5. I hope that makes sense to you. As for like the rest of the working out, all they're doing is literally just doing the normal distribution off of that. And I mean, we should be able to do that from literally 7, sorry, not 7b. I always say 7, it's not chapter 7, it's chapter 3. Chapter 3, part 2, 3b. Okay? Here's example 13 now. And this is another type of question, very similar type question to some of the exam questions, and it's asking us to calculate, first of all, the exact probability using the binomial, then work out the normal distribution, and then work out the percentage error. So I assume you can still do, so presumably you can also see this example 13, look in your pack, if you just pause the video and have a look in your pack if you think you can't really read this screen. I'm not sure how well the screen is coming across. So for part A, all they've done is the binomial distribution, and if you've got any issues with that, don't worry, we can revise that, but let me know. Part B, they do the normal distribution, and it's a good, again, an application of using mu as NP and sigma as NPQ, and just doing the normal distribution as you expect it. And I suppose the only noteworthy thing is a thing that we fought over a few weeks back. What is the percentage error formula? Here they've got, it is the actual minus the approximation over the actual times by 100. So what have they done there? I mean, also something noteworthy. Didn't I say to you before that for normal distribution, the probability of being exactly anything is just 0? So surely the normal distribution is just 0. Well, the thing is though, for binomial, a number isn't just a number, because if you're 50, you could have rounded up from 49.5, and you could have rounded up from 49.5 and rounded down from 50.5. So that gives you, well, a range, doesn't it? It's not just one number, it's the range from 49.5 to 50.5, which is what they've done the normal distribution on. So that's why you can give an actual number value for exactly 50, even though I told you in the past you couldn't do that for exact value for a normal distribution. So like the chance of getting exactly, I don't know, 4.3 would be 0, right? So what they've done is the continuity correction has given us mathematics, in that we can actually do something with these things. Because instead of just saying it's 50, no, we can say, no, it's from 49.5 to 50.5. Hope that makes sense.